In this video, we're going to talk about a new concept known as the mole and the conversions that you have to do with them. Unlike a lot of the stuff we've covered throughout the year, this topic will be entirely new for most people. This is not something you would have covered in a previous class. It is also a topic that is very crucial to a lot of the math and calculations we're going to be doing throughout the rest of the year. So a quick rundown of what our learning objectives are going to be. The first question we're going to try and answer is what a mole actually is. And I think I find for most students this is the hardest part of the process, is really wrapping your head around what this concept is all about. We're going to follow that up by doing a review of dimensional analysis. You need to learn, or remember I should say, how dimensional analysis works, because a lot of the conversion math we're going to do falls into that category. These are dimensional analysis problems. Then we're going to talk a little bit about the idea of molecular weight versus molar mass. Unfortunately, scientists tend to use these terms interchangeably when in actuality they do mean different things. We'll define both of them and we'll make sure that we talk about what those differences actually are. As we go to wrap this process up, the last thing we'll be talking about is dealing with the actual mole conversions themselves. We're going to create a flow chart that's going to show you all the different units you can convert moles into, as well as the conversion factors required for making those conversions. Then finally, after we understand what the conversion factors are, we're going to try a whole bunch of problems. And I got tons of practice for you here in the video, and there are likewise tons of practice problems you can be working on your own in order to develop a strong understanding of how this math works. As I mentioned already, this math is very crucial to the stuff we do throughout the year, so it's important that you have a very strong foundation. To start off today, I'd like to talk about what a mole really is. This is the topic I find actually that is most difficult for students. It's not the math we're going to be tackling later, it's simply the fact that the actual concept of what a mole is very hard for students to wrap their heads around. Secondly, this is also a very difficult word to define. It's one of those very fundamental topics, and trying to come up with one sentence that tells you everything you need to know can be very challenging. As a result, what I'm going to try and do here is come up with as many examples or definitions as I can, hoping that one of them is going to resonate with you so that you start to understand what's going on. My first definition, my first explanation as to what a mole is a way of keeping track of numbers of atoms or numbers of molecules. As we'll talk about later, the number of atoms or molecules is going to be very closely related to what we do in our balanced reactions, and the mass of those molecules is going to be closely related to what we talk about in the lab. And we have to connect those together. A mole is a unit that can do that for us. Another way of thinking about a mole is it's simply a quantity of things, just like a dozen is a quantity of things. We all know that a dozen means 12. If I tell you I have 2 dozen, we know that we're talking about 24 eggs. It's simply a quick and easy way to keep track of things like eggs. A mole is the same way. I can have 1 mole of atoms, I can have 2 mole of atoms, and in a minute you're going to know what I mean when I say 1 mole of atoms, just like you already know what I mean when you have 1 dozen. Now, unfortunately, we can't use 12 or a number like it to keep track of atoms or molecules because atoms and molecules are so very small. A mole must necessarily be a much larger quantity in order to very conveniently keep track of atoms. So to get an idea of what that quantity is, this is the number we're going to be using. And this, by definition, these numbers right here, and typically we're going to be focusing more on this number. This number right here is what a mole really is. It means 6.022 times 10 to the 23rd things. For those of you who are not super excited about scientific notation, here's that same exact value but shown in standard notation. And you can see, by the way, why things like scientific notation exist. This number would be ridiculous to write on a regular basis. But it does start to give you an idea of the scale of this number. Something I always like to point out in terms of comparison, we try and think of other numbers that we think of being very big. And a number most people think of as being very big would be the number 1 billion. If you have $1 billion, for example, you're pretty much set for life. You can see, however, that compared to a mole, 1 billion actually looks pretty darn small. And keep in mind that all of these extra places here don't mean adding in one more unit. They mean adding in, it makes this number 10 times bigger, this number will be 100 times bigger, 1,000 times bigger, etc., etc. We are literally talking about billions of things, just again to start to think about how large this number actually must be. Our last way of trying to define this term, this very difficult to define idea, is the point of a mole is its job is to link together the mass of a sample, which is what we measure in the lab, so we can actually notate that, the mass of our sample, which is how we measure things in lab, back to how many, a number of atoms or molecules, which is something that we do with our reactions. We want to be able to connect these two ideas and we need a unit that's going to connect it for us. And ultimately, that unit is going to be our unit of the mole. The rest of the video is then just guided towards figuring out how this connection actually works. Before we get too much further, it's important to realize that this number was chosen for a very specific reason. It's not just a random number, and the reason it was chosen is it has what we'll call a built-in conversion factor. Without this number, without 6.022 times 10 to the 23rd, you would have to do tons of extra mathematical steps every time you did a calculation, and it would make your life a lot more difficult. Luckily, the scientist who came up with this number, a fellow by the name of Avogadro, came up with this idea that eliminates a lot of that extra work. So let's talk about what we're dealing with here. For example, we can talk about an element. In this case, we'll talk about the element chlorine. You can take a moment right now and look up its mass on the periodic table, and we want to know the mass of one chlorine atom. So take a minute, pause the video, and see if you can find that. So looking at your periodic table, we'll find out that the mass of one chlorine atom is 35.4527. And if you recall from earlier in the year, the units on this would be atomic mass units. Now, the thing I want to talk about with this particular value here is the unit itself, and that's what's inconvenient for us. Again, we now know that one atom equals 35.4527 atomic mass units, and that would convert us between the number, which is really what we're talking about here, and the mass, which is really what we're talking about here. Unfortunately, though, this is not a particularly convenient unit of mass to use, nor is it a convenient unit to measure. Atomic mass units are trillionths of a gram, and we do not have devices that can measure that. Instead of measuring things one at a time, which is not typically what we do, we want to measure the mass of an entire mole of these things. And here's where the magic starts to happen. If we get a mole of these atoms together, they will have a mass of 35.4527 grams. And what Avogadro has really done here is he's built in a conversion factor that automatically converts us from atomic mass units into grams. So we kind of get this automatic conversion process. Without this, we would need to use a conversion factor every single time and convert this. Instead, what we've done is we've used a fancy number, this guy, that doesn't convert the number, which is what we normally do in conversions, but instead directly converts the units. So again, it saves us a lot of time and work. I don't expect you to know too much about this other than the fact that the number was chosen for a very specific reason, and it does a lot of good business for us. Now let's start getting into some terminology. I want to basically define the difference between what molecular weight is and what molar mass is. Both of these terms are ones we're going to use throughout the year, and as I said before, ultimately, sometimes they are confused with one another. Let's make sure we make some distinctions here. Let's start by calculating or determining what molecular weight is. This can also be used with molecular mass, although again there is a slight distinction between these two terms. Molecular weight is basically the total mass of a compound, the individual molecule. And that is calculated very simply by adding up the masses of the individual atoms involved. For example, if you have a molecule, for example, simply like H2O, we would get the mass of each hydrogen atom, we would get the mass of one oxygen atom, and we could add that all up. It'd be hydrogen plus oxygen. We'd get numbers off of our periodic table, and we'd get some sort of number as a result. That was our molecular weight. The important thing to note is when you calculate the molecular weight, we get an answer like before in terms of atomic mass units. But that's not really what we're interested in. This is what brings us to our next unit of molar mass. Molar mass is very similar, but instead of being the mass of one molecule, it's the mass of 1 mole of molecules. And as we saw in the previous slide, when you go from one molecule to a mole of molecules, you eliminate the unit of atomic mass units and you get into the unit of grams. But it's not really grams anymore, it's now how many grams there are per every 1 mole. And that's what we're going to be dealing with. Throughout the year, you might catch me using molecular weight and molecular mass, but almost always the term I really mean when I'm saying these things is going to be our molar mass. This is the number we use regularly. These guys do not have nearly as much of an application in an actual practical chemistry process. Let's take a minute and try calculating some molecular weights and as a result some molar masses. The first compound I'd like to take a look at is something very similar. We'll start with our good friend H2O, just like we were talking about on the previous slide. To find its molecular weight, we're going to need to know the mass of hydrogen and the mass of oxygen. Looking up on your periodic table, hydrogen has a weight of 1.00794, and oxygen has a weight of 15.9994. These are the tiny red numbers in the top corner of each box, and they are shown as atomic weights in the key of your periodic table. Well, to get the molecular weight of our compound, we're simply going to take these numbers and add them up. Unfortunately, though, we have 2 hydrogens, so we're going to take this mass and multiply it by 2. We're going to add it to the mass of the 1 oxygen we're dealing with, and we'll end up getting a total here. And that total is going to be somewhere in the vicinity of 18 atomic mass units. I did a little rounding here to simplify things, but we got this number, which is basically 16, plus this number here, which is 1 times 2, and we get the mass of 18 atomic mass units. Likewise, we can repeat this process with something different. We can take the substance sodium chloride. Again, we look up the mass of each compound. Sodium has a mass of approximately 23 atomic mass units. Chlorine has approximately a mass of 35.5 atomic mass units. We add those together, and I believe we get an answer of 58.5 atomic mass units. So again, it's just simply a matter of taking the mass of each individual atom and add them up. However, it's not typically the molecular weights that we are interested in. It is similarly the molar masses. But just like before, when you want to go from molecular weight to molar mass, the only thing that changes is the actual units. So this 18 atomic mass units, when we go into molar mass, is going to become 18 grams for every 1 mole. Likewise, this 58.5 atomic mass units is going to turn into 58.5 grams per mole. That tells us that for every 58.5 grams of sodium chloride, we have a mole of molecules. That means there'll be 6.022 times 10 to the 23rd. And for every 18 grams of water, we have a mole of water molecules as well. There'll be 6.022 times 10 to the 23rd of these guys. And again, what it's linking together is how many molecules we have to the mass that goes along with, in this case, that 18 grams. This now brings us to the last piece of the big puzzle today for these mole conversions. What we've identified now is what a mole is. We've talked about the fact that it can now convert between numbers and molecules. It's simply a matter now of putting this all together and identifying what our key conversion factors are and identifying what units we can get into moles from and what units we can get out of moles from. To do that, we're going to put together a little flow chart. In the center of this flow chart, we're going to have the unit of moles. And then connecting 2 moles, we're going to connect to all the other units we're going to be able to get into. The first unit I'd like to talk about, we can convert moles into a number of particles. Particles can be things like atoms, particles can be things like molecules, etc., whatever you want. We should be able to convert from moles into atoms and particles, and we should be able to convert from atoms and particles back into moles, and the number that we're going to use to do this is the number we've been talking about all along. There are 6.022 times 10 to the 23rd things for every 1 mole. So for every mole we have, we're going to be 6.022 times 10 to the 23rd things. You're going to use your dimensional analysis tools then to decide whether it's moles over things or things over moles. And as I said before, things can really be things like atoms, or they can be molecules. Just like a dozen, you can have a dozen of anything. We can have a mole of anything, but again, typically atoms and molecules are what we deal with. So that's one of our conversions. Another conversion we're interested in, we can convert moles into a mass in grams. And this by far is going to be the most valuable conversion you use. You're going to, 3/4 of the time, I would say this is the one you're going to be working with. So mass in grams is the next thing we can convert into. Again, we should be able to convert from moles into a certain mass. Typically we do this when we want to be able to compare it to lab results. Or we can take a mass and convert it back into moles, and we use this conversion when we want to compare our results back to balanced chemical reactions. Now, unlike moles to particles, there's not a number we can use here. To get the conversions here, we need to use the molar mass of our compound. We need to use the molar mass of our compound, and we get this information from our periodic table. And what's important to note here is that this thing has units. It's always going to be in some number of grams for every 1 mole. And this is going to be the conversion factor we're looking for. But it's important to note that you have to calculate this conversion factor every time for every different substance you're using. Our last conversion we're going to be dealing with is converting moles into a volume of gas at standard temperature and pressure. A volume of gas at standard temperature and pressure. We'll talk about what this STP stands for in a second, but for now let's talk about the conversion. We can go moles into that volume of gas, or we can take that volume of gas back into moles. This is used very commonly, again, when you're dealing with the results of an experiment. If you get a solid product or a liquid, we usually refer to how much mass we have. If we get a gaseous product, it's easier sometimes to record the volume of it as opposed to the mass. And luckily, this conversion is actually relatively straightforward. There are 22.4 liters of gas for every 1 mole of molecules. So for every 6.022 times 10 to the 23rd molecules, it's always going to take up the same volume, which is 22.4 liters. We'll talk later in the year about gases and how they behave, and that will come back to this idea and talk about why this number works. Before we move on to actual problems, let's talk about this term STP. What it means is standard temperature and pressure. And what scientists have done is they've identified pressures that they consider the standard lab conditions. The standard pressure is in unit of atmospheres, and it is 1 atmosphere pressure. That's the pressure you're feeling right now. And the standard temperature is 0 degrees Celsius, which is a little chilly, but again, it's considered the lab standard thing. The reason this is very important is the fact that gases' volumes change when you have different pressures and different temperatures. So this factor here is only true under these conditions, under 1 atmosphere and 0 degrees Celsius. Again, when we go later in the year and talk about gases in more details, you'll be able to calculate the volume of a mole of gas at any temperature and any pressure, but for now, we're going to stick with just this. In short, you don't need to know a whole lot about this. The thing I would watch out for is you see this term STP somewhere. That usually means you're going to need to use this conversion factor at some point. And that's really as far as it goes. Before we dive into actual problems, I want to talk about the fact that these mole conversions we're about to do require dimensional analysis, which is what we tackled way back in the beginning of the year, way back in September. If you do not remember how dimensional analysis works, I very strongly recommend you take a little bit of time to go back and look over that material. In brief, we're going to talk about this here. Now, the flow chart we talked about before provides you with our new conversion factors. The question you need to answer, and which recalls, is how do I use those conversion factors? So let's talk about an actual practice problem we can show this in, just so we can recap the process of how these conversions actually work. We can start with the unit of 20 miles, and we put in a multiplication sign and a line. We want to get rid of this unit of miles, so that means we have to put miles down here. You have to think about what you can convert miles into, and I don't know about you, but I can convert miles into feet. There are 5,280 feet for every 1 mile, and the way I've lined things up is going to cause miles to cancel out, and now I'll have an answer in feet. And then I can continue that process by putting in a new conversion factor. Now we want to cancel out this unit of feet, which means feet has to be down here. We can convert feet into the unit we want, which is inches, and I know that there are 12 inches for every 1 foot. Quick second with your calculator, we get 20 times 5,280 times 12, and I get an answer of 1,267,200, and that wasn't 1,000, that was 1,267,200 inches, which if we round down to the correct number of significant digits, we're really talking about somewhere in the vicinity of 1 million inches. The answer itself is not important though. What is important is that you remember how this process works, how we cancel out units, how we line things up, because it's exactly what we're going to be doing now, but instead we're going to be doing it with our new conversion factors. So all that's left now is working on some practice problems. I'm going to go through one of these on each page just to give you guys a little chance to do it. I encourage you to try the others. They're all going to work in a very similar fashion. So for this first group of problems, we're going to be converting the following units into the unit of moles. So for example, in this first one here, I have a certain number of atoms, and I want to convert that to moles. If you go back to your flow chart and you put your fingers on the unit of moles and you put your fingers on the number of things, a certain number of atoms, you find out that the conversion factor between the two of those is our number, 6.022 times 10 to the 23rd. So really quickly, I can put in a multiplication sign and a line here. I know down here must be atoms, and up here we're going to have the unit of moles. And according to our chart from before, for every 1 mole, there are going to be 6.022 times 10 to the 23rd atoms. According to the way we've lined things up, atoms cancel out with atoms, and we get an answer in a unit of moles of silver. Likewise, you can repeat the process with each of these. Just notice that when we're doing these conversions, if you start with the unit of grams, you're going to do something different. If you start with the unit of liters, you're going to do something different. And that something different is what conversion factor you're going to use. You should take a minute right now using your flow chart from before and see if you can't try a couple of these, converting from grams to moles and converting from liters to moles. And then on the next page, I'll obviously go over the answers. So really quickly, here's the answers that we got with each of these. We converted our number of atoms into a certain number of moles, and we found out we got a very small number of moles. And likewise, we got the answers for the gram to mole conversion and the liter to mole conversion. Really quickly, to show you how these work, we can do this for silver. If we want to convert from grams of silver into moles of silver, we need grams down here at the bottom so that grams cancel out. And again, we're going to have the unit of moles on the top. Well, this unit, unlike here, isn't just a number. This is something we have to look up on our periodic table. It turns out that there are 107.8 grams for every 1 mole, and this came from our periodic table. When you do that math, we end up getting an answer of 0.2201 moles of silver atoms. And then finally, we can do the same thing here. In this case, it's asking for liters of gas. We put in our conversion factor. Liters has to be on the bottom, and again, moles are on the top. Liters now cancel out with liters to get rid of that unit. And we know from our conversion flowchart that there are 22.4 liters for every 1 mole of gas. Again, you do that math, 32.67 divided by 22.4, and we get about 1.5 moles. We can try a couple more of these. Again, it's the same process of using the flowchart and using your dimensional analysis skills. Just to take a look at one of the group of these, I'm going to let you work on the others on your own. Let's try the last one here, which has us going from liters of gas into a certain number of grams. This is a situation where the problem is a little bit more complex. If you look on your flowchart, there is no conversion factor that goes from liters directly to grams. What we can do is convert liters into moles, and then we can convert moles into grams. So we're going to have to actually do this in 2 steps. And that's actually one of the other values of this unit moles, is it connects units together that otherwise would have no possible link. So for example, we can go here. The unit we're trying to cancel out now is the unit of liters, which means I have to put liters on the bottom. I can convert liters into moles according to my flowchart by saying that there are 22.4 liters for every 1 mole. Liters now cancel out. And then I can do a second step here that converts my moles into the units of grams. Every 1 mole, we have to look at the gas Cl2. Each chlorine atom has a mass of approximately 35.5, which means that the mass of my Cl2 is approximately 71. And again, this information is coming from our periodic table. So there's about 71 grams for every 1 mole. That's our molar mass. Moles cancel out with moles, and now it's calculator time again. 12.13 divided by 22.4 times 71 gets us an answer in the vicinity of 38.44 grams. And if we go to the next slide, that's about what we get there, 38.44, depending on how much you did your rounding there. Likewise, I have the answers for the other 2 here. Hopefully at this stage in the game, you should be working on these calculations on your own. Set them up in the same way and use the flowchart to decide which conversion factor gets each of those done. For my last round of examples here, we're going to convert into some of the units we haven't talked about as much yet, converting into liters and converting into a number of particles. Again, I'll do one of each of these, and I'll leave the other ones for you guys to try on your own and work on. So the first one we'll take a swing at here is converting from moles back into liters. This problem is relatively straightforward. We have 4.5 moles here. We need a conversion factor that gets rid of the unit of moles and gets us into the unit of liters. By putting moles in the bottom, they'll cancel. We'll get the unit of liters on the top. And again, your flowchart tells you that there are 22.4 liters for every 1 mole. We can do our math there and get ourselves an answer. Let's take a look at one of the problems at the bottom for a second. Again, now we want to get into number of particles. We'll try the second one here. 73.1 liters, 414 liters of neon gas at standard temperature and pressure. Again, this STP doesn't do a lot for you other than let you know we're probably going to be using that 22.4 liter conversion. So we get 73.14 liters. Our first conversion, unfortunately, we can't get from liters directly into a number of particles, but we can say that liters can convert to moles, just like we did above. 22.4 liters is equivalent to 1 mole. Notice that chlorine gas and neon gas have the same number. The gas type is independent. Its volume is independent of the type of gas that's made. That cancels out liters for us. Our second step then would be to convert from moles into number of particles. We know that 1 mole, line it up so that these cancel out, is equivalent to 6.022 times 10 to the 23rd atoms in this case. In the previous problem we did, it was molecules. This time, since we're talking about atoms, it's atoms. We could take a look again at our answers. We find out for our first problem that 4.5 moles of chlorine gas gives us approximately 100 liters of gas, although our significant digits don't perfectly match up there. And the last problem on the page that we worked on together gets us an answer of 1.966 times 10 to the 24th atoms. That is a very huge number, but we're talking about numbers of atoms, and we always expect our numbers of atoms to be very big. You can see the same exact thing happened up here with this answer. Altogether, this is something, just like before, you need to practice. We had to practice with naming and we had to practice with balancing. These are conversions you need to get comfortable with. If they didn't make sense here in the video, we'll be talking about these again in class and going over some problems together until they do start to make sense. But like anything else, it's simply a matter of practicing the content. In terms of getting that practice, if you look to the bottom of the screen on the website, there are a couple links to some problems that have practice with them, as long as the answers to go along with those. Between that and what we work on together as a group, I think this is something you'll find is not overly challenging.